polynomials and computation. So I initially thought to call it polynomials in computation, but these things just go so hand in hand that I cannot really say polynomials are being used in computation. That is just that they appear in computation quite a bit, and that's what I really want to tell you about, how polynomials appear very naturally in computation. It could be a practical task and I will show you some examples, or it could be a theoretical question which we will also go through a little bit more. I am more experienced in theoretical aspects of it, but I will definitely try to do some justice towards practical applications as well. So anybody who does not know what a polynomial is, just the definition, nothing more about it. Everybody knows what a polynomial is. Now can you try to guess some practical real life application of polynomials in any part of computer science? And if you know, well and good, or otherwise could you try to guess where they might come up? So I will tell you a very interesting example. I am sure many of you have done UPI payments, or maybe you have used QR codes somewhere for going to a website, looking at a location or whatever. There are many places where you might have seen a QR code, you scan it and you are able to go to some website, you are able to do some payments, and many other such areas end up using QR codes. Now some of you might have noticed that, let's say I am standing at a shop, there is a QR code and many times they are damaged. There might be some paint peeling off, or you are not actually able to get a very clear picture, you just get a partial picture out of it, and still you are able to go to the correct website, you do the payment and it reaches to the correct person that you want to. So how can this be that without actually looking at the whole picture you get the information that was actually put in that whole picture? So what is a QR code? It's just some black spots here, white spots here, so that just encodes some information. You can see it's some kind of a binary representation, 0 1, but without looking at the whole representation you are actually able to say what information there is in that QR code, and the answer for why you are able to do it is actually based on polynomials. So I will first define what a polynomial is, just to be complete, and I will not properly define it. I will just say, so let's say you have just one variable. So this is something that we are quite aware of. We have studied quadratic polynomials since we were kids, essentially, like in 7th or 8th class maybe we have studied quadratic polynomials. So you might have seen something like x square plus 2x plus 1, and you can actually write it as x plus 1 whole square, and something like this will actually be useful in the next part of what I am going to talk about. In general you could just say that there is some x to the say d times some number, let's say ad, plus ad minus 1 x to the d minus 1, so on and so forth till a0, and I am just going to put this constraint that ad should not be 0, because if it is 0 then I can just ignore it, go to the next one. So I am just going to put this constraint, ad is not 0, and this number, what is it called? Degree of the polynomial. Now you will see why the degree of the polynomial is such an important object to consider. So the degree of this polynomial is d. Now some interesting fact that you know about the polynomial which has something to do with the degree. Does anybody know any such fact which has something to do with degree?
Number of solutions.
Exactly. So let's say I want to ask how many points there are such that px is 0. How many can there be? Right? So let's say, in other words, I take a set of points a which is a1 to ad plus 1, right, and they are all different points. Can I say something about the value of the polynomial in all of these points together? I know that the polynomial can be 0 on at most d points, What does that mean? On one of these points it's not 0, exactly. So we can write it like this, that P of ai is non-zero for some I. Now this fact will actually be very useful in some of the things that I am going to talk about. I will not go into the formal details. Actually in this talk you will not at all see any proofs, any formal proofs at all. It is just an exposition to polynomials. But now you might ask, why is such a fact so useful? So now I will have to go to a little bit more generalization. So I will talk about polynomials which have many variables, let us say x1 to xn. Even here it is not hard to define what a polynomial is, so I will just look at an example. So you have some x1 square, x2, x3 plus something 3, x1, x4, x5. Essentially just take powers of the variables, multiply them together and then add them up, you get a polynomial. Now just like there is something about a polynomial on one variable being 0 on d many points, you can actually say something about the polynomial being 0 on an n dimensional grid. So instead of just a set, you will actually have an n dimensional grid. So let us say, so I am just going to draw a picture. So here what the situation was is like you took these points and you were able to say the polynomial must be non-zero on one of those points. Just because you know that the degree is d, it must be non-zero on one of those points. Here I am actually going to have a grid. So let us say I have this grid and imagine it is in n dimensional. I cannot draw n dimensions here, but let us imagine that it is. And if it is big enough, then again I can say that on this grid I can find a point on which the polynomial must be not 0, non-zero, non-zero. Now how does all of this come into the picture when I was talking about QR codes, right? You might say that okay, all of this theory is nice and all, but what about QR codes? So now the next thing will be, let us look at two different polynomials. So let us say you have P1 and P2 and both have degree, let us say they are equal, their degrees are equal, degree d, but the polynomials are not equal. And now I want to say how many points can there be such that they are equal. So does anybody have an answer for this? Why? I mean not necessarily d minus 1, d, right? Because what you are saying is I am just going to look at the difference of the polynomials p1 minus p2, this also has degree at most d, and so this can be 0 on at most d points. So just like that I said something about multivariate polynomials, n dimensional grid. So a very analogous statement you can say about multivariate polynomials, difference of two polynomials on a n dimensional grid. So now you have two polynomials, you know that they cannot be equal on all points as long as I have a large enough grid. They cannot be equal on all points, they have to be differing at one of the points. Now let us say that actually I take a much larger grid, not just this small grid, but much larger grid. So I have, let us say degree is d, let us say I take a grid of size d square. Now again the same thing will hold, which is at most on d points these two polynomials can be equal, so on all others they must be not equal. And this is the property that is used in QR codes. So what we are saying is, you look at a you encode your information as a polynomial, you encode your information as a polynomial. So you have this huge QR code, and on this you have put what is the value of a polynomial on different points. So you have said, okay, it's 0 here, 1 here, it's somehow encoding the value of a polynomial. But you are only actually getting to look at a small part of it, not really getting to look at the whole part. But as long as this is large enough, I know that two polynomials cannot be equal on this whole thing. So just by looking at the values here, there is exactly one polynomial which can take all these values. So now the question is, if you know there is exactly one polynomial, how do you find it? For that there are algorithms. Now going to that will actually take up the whole lecture and many more. So I won't be able to do that. You can go to Wikipedia and read something about Reed-Solomon codes, and this is exactly what is used in QR codes. So you can go read about Reed-Solomon codes and how they are useful in implementing QR codes. And the crucial thing you have to remember is, you do not have to look at the whole QR code. It could be damaged, it could be a blurry picture, it could be a partial picture, still you will be able to get the information that was all encoded in there. So this is one interesting application of polynomials. Now there are many other applications of Reed-Solomon codes, and in general it comes into an area called coding theory. Now these codes are not like programs, these are not programs. This is a specific word used for a specific mathematical object in which such a thing holds, that if you look at two different objects, they will not be the same on many points. They will be same on a few points, on all others they will be very different. So you start, let's say, with d square many points. Here the points may be very close to each other. One of them could be saying 0 1 0 1, one of them could be saying 0 1 1 1. They only differ at one position. But now when you take all the values of a polynomial, you look at the whole list of the values of the polynomial, there will be very few places where they actually match, and all other places they will not match. This is exactly what a code is supposed to do. So again, I am not going to for formal definitions. You can go to Wikipedia, you can read about Reed-Solomon codes. There is a lot of other literature talking about coding theory. So if you just search coding theory, like, you will get thousands and thousands of results. So you can go read them up, but this is one interesting application. And very similar things are also used when satellites want to communicate with the earth, because you have the atmosphere, they will send some signal. That signal will not reach as it is, they will send some bits, some of it will be lost, some of it will be corrupted, but still using that partial information you will be able to gather what that satellite was trying to say, what was it trying to communicate. And then yeah, so for example, like CDs and DVDs are really old now, but they also used to do the same thing. They would encode the data using codes, and if you remember that sometimes DVDs you really used to get really scratched, and still they worked. So it looked very miraculous, that how is it happening, and all of it has to do with codes. Now there are some interesting applications of all of this theory as well, so I will talk about that a little bit. So let's say I am a teacher, you are a student, and I have some interesting theorem I want to prove to you. So what I will do is, because I have much more knowledge supposedly, but let's say I do, I want to say that this theorem is true, I will write down a proof for you, and because you do not know the proof, the correct proof, you will look at it step by step. So I have written down on this huge page a lot of lines, and you will look at each of these lines and be satisfied that okay, this is the correct proof, or not be satisfied. So let's say I want to prove to you the Pythagoras theorem, or any favorite theorem of yours. I will write down a whole list of statements. You will say, well, one statement follows from the other, so I am happy, it works. But you have the time to actually go through this. Your teacher does not, he is very busy, or she is very busy, and you write down a long answer in your exam. The teacher does not want to go through the whole answer. They only want to look at a few lines and still be satisfied that what you've got is correct. So there is actually a theorem called the PCP theorem. So now there are, if you search for PCP, you will get two different things. So I will just spell it out what it is. It's called a probabilistically checkable proof. But what it essentially is saying is that if a teacher wants to just be convinced, like not necessarily that the answer is definitely correct, but just that okay, there is a high chance that the answer is correct. Maybe the answer is a little bit wrong because I have not looked at the whole part of it, but just a small part I looked at and I realized that probably it's correct. If I just want to do that, I can just look at few lines, and what that few means is, does not matter how long the proof is, I will just look at some randomly chosen 10 lines. So let us say I will just choose 10 lines. Just by looking at these 10 lines from potentially hundreds of thousands of millions of lines, could be very long, just 10 lines, I will look at it, I will be almost sure that your answer is correct. So I can save a lot of time. Now of course the technical statement is much more technical, so but this is the gist of it, and again this ends up using coding theory. Now what is it using about polynomials is that, let us say, to describe a line to you, how many points do I need to give you? 2 points, right? So similarly, let us say there is a quadratic polynomial, I want to describe it to you, how many points do I need to give you? 3. So in general, if there is a degree d polynomial, so there is a degree d polynomial p, I want to give you a bunch of points so that you can uniquely identify what the polynomial is, I will just give you d plus 1 points. So this is the case for univariate polynomials. If you have multivariate polynomial, I can actually give you d plus 1 to the n points, and you will know exactly what the polynomial is. But an interesting thing is, if I just want you to be sure that okay, the polynomial is not exactly this, but maybe it is probably this. Again, I do not want to be exactly sure, just okay, it is probably this. I just need to give you very few points. If I give you very few points, just by looking at the values of the polynomial on those points, you can actually figure out probably this is the correct answer. And this is exactly what goes into proving this statement. Of course, it took a lot of work to prove this statement. So you can go through their actual work, there are many expositions. So actually I will tell you the list of authors if you want to go through it. So there is, so this ultimately what settled this question was a work of Arora, Sudan and Segedi, but yeah, of course I would not recommend going through the original paper. There are many good expositions for it. There are many good lectures on YouTube, so you can really find out about it from various sources, and there are various good expositions, but it's actually very advanced stuff. So if you want to go through it, take your time. Yeah, and you cannot verify what they are saying by just looking at few seconds of their videos. We'll have to look at the whole of it. And now there is one more application called property testing, which I will actually come to if I have time at the end of my talk. Although it is the most interesting to me, but it's the most theoretical application of it. So I will probably come to it if I get time. Now there are some other very interesting applications outside of computer science as well. For example, I mean, this is computer science, which is, let us say you want to send some data over the internet. So let us say two servers are talking, they want to talk to each other, but they know that internet can go a bit wonky. It might not really send what they are trying to send. So it's, you can again see it's very similar to satellite communication. So they end up using codes to be able to communicate properly, so that they know that even if there is a bit of corruption, they will actually get through what they want to say. And because polynomials are such nice objects, so for example, I am sure at this point you might know what are differentiable functions, what are continuous functions, but sure all of you know what these are. And polynomials are everything, right? You can differentiate them, they are always continuous, so they are very nice function, they are always continuously differentiable, they are very nice functions to analyze. So if you can actually say something is modeled by polynomials, so for example, you know about the stock market, right? So some of you might know what are stock options, but even if you do not know, just okay, there is something called stock options, and in general understanding them is very hard. How do they behave? But you can actually model them as polynomials, and it's called the Black-Scholes model. They say, well, I will just approximate it by a polynomial, I don't need to know exact price, nobody can know the exact price. How will the market behave? Who knows? If I knew, I would be the richest person in the world. But they just say, well, I will approximate it by a polynomial, but now polynomials are nice, so I can study their derivatives. So they study their different derivatives, they have some parameters, and with those parameters, if you know what Greeks are for options, maybe some of you know, maybe you don't, but if you do not know, it's fine, just understand that they convert it into a problem about polynomials, and then their life became really easy, and these guys actually became quite rich. They were string theorists, and this is a joke that a pizza can feed more people than a string theorist. It may not be true, but it's a joke. But these guys actually made a lot of money because they were able to figure this out, and they went into the stock market and really started this whole area of algorithmic trading, in which I have worked quite a bit, but this is what they do. So they were actually able to make a lot of money. And if you have heard a little bit about cryptography, security, which is secure transactions, so I am sure many of you have started using debit cards now. So they use what is called an elliptic polynomial. Now what that is, again I will not say, but again it has to do with a very nice polynomial. And why is that needed? So on your computer, when you are doing something over the internet or satellites, they have a lot of data to transmit, so they can afford to use more bandwidth. But on your debit card, there is a very limited amount of data to store. There is a magnetic strip which can store some little bit of data, but it actually has to end up storing a lot of data in a very robust way, and elliptic polynomials actually end up helping with that. So now all of these things, again there is very interesting theory behind it, they have hopefully interesting to you applications as well, and these are things that you can find out very easily about on the web via Wikipedia or some nice expositions. If you just search elliptic curves, again lot of results will come in. So now this is already a lot to do with practical life, but now let's come to a little bit of theoretical aspects, because that's what I am more familiar with. So right now I was just saying how polynomials are used in tasks of computing, but let's say I want to talk about how do I compute polynomials. So the next thing is not how do I use polynomials in computation, but actually how do I compute polynomials. So what are you allowed to do? You can start with a variable, let's say you start with x1, you can multiply it with a, let's say a constant, so you multiply it with 2, you get 2x1. Let's say you start with some 2 other variables x2, x3, you are allowed to add them up, you get x2 plus x3. You have, let's say, another variable x4, and you are also allowed to multiply them, so you get x2, x4. And not only this, you can use all of these intermediate steps that you achieved again. So you can use this again, multiply these two out, get 2x1 times x2 plus x3, and let's say you do some other steps, and you will finally end up with a polynomial. Is that clear? So you will end up with a polynomial. So now there is a very natural question, which is, given a polynomial that I want to compute, so you take your favorite polynomial, you want to compute it, but the only way that you can do it is this: you start with the variables, add them up, multiply them together, multiply them with a constant or whatever. You can even subtract, because you can use negative constants, you can use -1. So you can do all of these operations, you can use your intermediate calculations, but you do not want to do too many calculations, right? You don't have the time. You only want to do a few calculations and arrive at your favorite polynomial. And as it turns out, this is a very fundamental question. How do you compute polynomials using these operations? And some of you might be aware of this question, which is, you are given a natural number n and you just want to check whether n is prime or not. Prime or not. And for a long time it was open whether we can do this fast or not. The algorithms that we knew to check whether a number is prime or not were actually very slow. For example, you might have seen the sieve algorithm, right? You just go through from 1 up to square root n, you go check if it is dividing, and it will take square root n time. But as n grows, this is a lot of time, because a number you can actually represent by very few bits. How many bits do you need to represent a number? Let us say the number is n, how many bits would you need? Not n bits, log n bits, somewhere around log n bits. So if n is really large, let us say n is like 2 to the 100, you only need 100 bits, but how much time do you need? 2 to the 50. 2 to the 50 is really large compared to 100. So this naive algorithm, sieve algorithm, it is not so surprising that it is not so fast, but it is not. And in fact, a lot of other ideas that people came up with were not fast. We did not know fast algorithms for a long time, until 3 Indian researchers working in India, in fact in IIT Kanpur, Maninder Agrawal, Neeraj Kayal and Nitin Saxena. So they gave this algorithm in a famous paper called Primes is in P, whatever that means, but they gave a very fast algorithm for checking whether a number is prime or not, and it actually had to do with how do you compute a polynomial quickly. So they figured out that there is some polynomial that if you can actually compute quickly, then you can check whether a number is prime or not, and via that algorithm they were able to prove this result, that there is a fast algorithm for checking whether a number is prime or not. And in fact, it is interesting to know that they were both undergrad students. Neeraj Kayal and Nitin Saxena were both undergrad students when they did this work. Of course, Maninder is a famous professor at IIT Kanpur. So they were working with him and they got this result, and more or less just for this result they got a PhD within 6 months of getting admitted. So if you do something like this, you will get essentially for free a PhD. So you should feel a little bit motivated. If you are in undergrad, you should feel a bit motivated to work on some problems like this. And if you are a PhD, still you should feel motivated, because you will be able to graduate much faster, right? And then the whole world will know who you are. So this is one very nice example of polynomial computation. How do you compute a polynomial being useful in something which is a very natural problem, whether a number is prime or not. So now this actually covers the popular part of my talk. Now I will come to a little bit boring part, so I will go a bit slow. If you have any questions about any of this, of course you can feel free to stop me right now and ask. The same goes for the rest of the talk as well. Do you have a question? Okay, sorry. So the same goes for the rest of the talk. Now I will go a little bit more slowly. I will go a little bit more in detail. We will see some results but no proofs at all, okay? And if at the end any of these, one of these things you find interesting, I will be happy. So now I will actually come to the area that I work in, which is called computational complexity. So some of you might be aware what that area actually is. but I will first give like a gentle introduction to what computational complexity is about. So Turing machines is something now most of you have been introduced, right, in the previous lectures. So in a Turing machine, let's say I give an input x and I wanted to compute some function of x. Let's say I wanted to know whether x is a palindrome or not, right? This is a very simple function. Then I can ask how many steps does it take. So I will denote it by t of n. How many steps does it take if x had n number of input bits? How many steps does it take to determine this property of x, which is whether it is a palindrome or not? So palindrome is easy, so you can see that this will not be a very large number. I mean, you can very easily see you can do it in n square steps. Just go back and forth, n square steps you can very easily do. You can of course do much better. But now there are many problems. For example, primes at one point was one of those problems where we do not know how to do these things quickly. Another example I would give you is, it is given a number n, again as a binary string. So you are given a number natural number n, and you are just supposed to tell me is there a prime p1 such that it divides it. Sorry, no, not this. You are supposed to output a prime p1 that divides it. So it's not about checking, it's about giving me a prime that divides it, and divides it non-trivially in the sense that this m is not 1. This is called factorization, right? This is what factorization is, and we do not know if there is a fast algorithm for this. And in fact, one of the most widely used cryptographic systems, if you have heard, RSA algorithm, is actually based on this, that we cannot factor quickly. And if you have heard of quantum algorithms, we also know that quantum algorithms can do this quickly. So there is a Shor's algorithm which allows us to do this quickly. But now the question is, let's say I believe that this cannot be done quickly at all. No matter how clever you are, does not matter. There is something about this problem which allows me to not be able to do it quickly. How will you prove such a statement? So you have already seen some examples. For example, the halting problem you have seen, it cannot be done at all, right? So you saw a proof that you cannot do halting problem at all. But let's say you just want to show that, well, this cannot be done quickly. So this should be an easier task, right? For the halting problem, you are trying to say there is no Turing machine. Here I am just trying to say there is no Turing machine which is fast enough. This should be an easier task. But so as far as we know, it is not. In fact, there is a very famous conjecture, if you know, that P is not equal to NP. And if you solve this, not only do you get fame, you also get $1 million. I mean, you literally get $1 million if you solve this problem. And this is exactly what complexity is about, which is you want to show that certain functions are somehow inherently hard for a computation model. For example, Turing machines is your computation model, and you want to show that factorization is hard for it. So now, how do you prove such a statement that something does not exist? If you want to prove something exists, let's say you are saying something can be done quickly, how will you show it? You will just say that this is the procedure, look at this procedure, you analyze the runtime, it's fast, we are happy. But how do you prove something cannot be done?
Counter example?
In what sense?
If someone says that it exists, you give a case where it fails.
But now you want to be able to give counter examples no matter what the other person says. If they say this is the algorithm, you will find a counter example. If they say this is the algorithm, you will find a counter example. But how will you prove to me that no matter what algorithm they have, I can find a counter example? How will you prove this? It's a mathematical statement, right? You have a mathematical statement that there is this set of all tasks that I can do quickly, and there is this other task which is not in this set, right? So these are all, so let's say this is the class P, and there is some task, let's say factorization. I want to prove that it's not here. How do you prove such a statement? Yeah, exactly. So that is what I'm coming to. Yes, exactly. That's what we have to do. So now how do you do this? One of the ways is you look at all problems here and you associate some number to them. There is some number that I am going to associate. I will give you examples later. So I will just associate some number to them, some real number r. And I will say I will look at the whole set R that I get for these problems. So let us say I get this set for all these problems. And now what do I have to show for factorization? How can I show that it is not here? Anybody? Any clue? So let us say I associate a similar number to factorization, but if it is not in this set, then I am done. Does that make sense? So if I associate a very similar number to factorization and it is not in this set, then clearly factorization cannot be in this set. So this is a very common theme, not only in computer science, it is also a very common theme in mathematics. So this is called what is called a measure. Forget about the word, but it's just you are associating some number to the objects that you want to study, and you are saying this other object associates with a number which is not in this set, then clearly this cannot be here. So now I will actually give you some examples of where this happens, but for me to do that I will have to introduce some notation. So just bear with me, we will go slowly through it. Yeah. So binary values I am assuming you guys know, just 0 1, right, and logical gates like AND gates, OR gates. Even if you do not, I will define what they are. So the things that I am going to talk about are called Boolean functions, and Boolean because they were studied by somebody called Boole. So that's the only reason they are called Boolean functions. So they have n inputs, x1 to xn, and they are allowed to take 0 1 values, and the function is supposed to output a single 0 1 value. Now it's not hard to see that whatever computational task you want to study, you can actually think of it as a Boolean function. Even prime factorization or whatever, all of them you can think of as a Boolean function. So the task of complexity theory is to say that I can collect functions in a set. So you have this big universe of all functions. I will say, well, look at this small interesting set of functions, and then I will find some other function g which is not here, and the way to do it would just be exactly how I did it here. You find some measure, you associate that measure to this set and prove g does not belong to that set, the measure of g does not belong to that set, and you will be able to prove this result. So now we will go back to the starting of the talk, which is polynomials. So you will say, well, why are you talking about all of this? You said you will talk about polynomials. So I will show you where polynomials come in. So you take any Boolean function, you can actually write it down as a polynomial exactly. What I mean is, you take a Boolean function f, you can write down a polynomial p of f, let us say, such that f of a equals pf of a for any Boolean point. And what is a Boolean point? It just takes 0 1 values. So I can evaluate my function f at this point, or I can evaluate the polynomial at this point. They will give me the exact same value. If f is 0, p is 0, if f is 1, p is 1. Now what's an interesting measure about polynomials? Sorry? Okay, so we will go into that later, okay, but for now just it is some polynomial. Now what's some interesting measure of a polynomial? This is something I defined, degree, right? So this is exactly what we are going to study. Associate to each function a polynomial, study its degree, and that will be the measure here. But the way we associate these polynomials will keep varying, and they will give us different values of the degree, and those different values of the degree will allow us to prove different results, and I will then show you some of those results, what they are, not how they do it, just what the results are. Okay, so we will go through some of the examples of how people use association with polynomials and their degree to prove some results in complexity theory, some impossibility results that you cannot do this at all. Okay. Now as it turns out, so this is a question associated with the question that he asked. So if do you know what fields are? Group theory a little bit. So some of you might know, some of you might not know. That's why I really do not want to go into it. But over some structure which is called a field, but you can forget about what a field is. Over some structure which is a field, this is actually unique, which is if I tell you what f is, you will only be able to find one pf, and you will always be able to find that one pf, always one and at most one. So to each function you can associate a unique polynomial, and then you can ask what is its degree, right? So you start with a function, you construct the only polynomial that can represent it, and you ask what is its degree, and that will already tell you a bunch of things. For example, so there is a very simple computation model which is exactly like how we work in real life. You start with something here. Let's say you want to go to school. You will say, well, is this road open or not? If the road is open, I will go to this road, otherwise I will go to that other road. Is there a bus coming on this road or not? If it is coming, then I will get on the bus, otherwise I will look for a cab. And here you might say, well, now do I have petrol in my motorcycle or not? If I do, then I will go by the motorcycle, otherwise I will not, right? So at each point you are looking at the situation and making a decision out of it. So does anybody know what this is? Decision tree, right? So decision tree is something you might have already encountered, and they are very natural objects. They are just saying, I will look at what the situation is. Well, is there water on the road? If there is water on the road, I will rent a boat. And you may not get it, but yeah, you will try. But this is a decision tree, and as it turns out, the degree of this polynomial is very intricately connected to what decision tree you can form to calculate f. So just like we did here, what you will say is, let me look at x3. Is x3 0 or is x3 1? If x3 is 0, I will go to the left, otherwise I will go to the right. Then you might ask, well, is x1 0 or x1 1? Or here you might ask, is x2 1 or x2 0? And you will keep looking at what are the values of the inputs, keep making decisions, and in the end you will either say, well, my function is supposed to output 0 or it is supposed to output 1. This is a decision tree. And in the decision tree, the important question is, how many decisions do you need to make, right? If you have to make a lot of decisions, it's going to be really irritating. You will just say, well, I will not go to school today. So you want to be able to decide this quickly. You want to have as few decisions as possible. But as it turns out, the minimum number of decisions you need, you have to make, is actually equal to the degree of this polynomial, which is unique. So if I give you a function, let's say I give you the AND function. What is the AND function? It's just saying that A should be all ones. Sorry, A should be all ones. Then I will output 1, otherwise I will output 0. And I want you to construct a decision tree for it. So there is a very simple way to do this. How will you do it? How will you check all the inputs are 1? It's very simple, just
x1 equal to 1 and equal to
exactly. So you will say, is x1 0? If it is 0, output 0, because I do not want it to be 0. If it is 1, look at x2. If it is 0, output 0. Otherwise, keep doing this. At the end, you will get, well, all of them are 1, so I will get the output is 1. And how many decisions do you need to make? Exactly as many as the number of the inputs. But how will you show to me that this is the minimum number of decisions that you have to make? There is nothing you can do better. The way to do it is construct this polynomial for the AND function, and for the AND function this polynomial is very simple. Can anybody guess what that polynomial is? So it is supposed to give exactly. So you just multiply all of them together. Multiply all of them together. If any of them is 0, what will this give? 0. And if all of them are 1, that's exactly what I want. So the unique polynomial that represents AND is this polynomial, and as I told you, it's unique, so there can be no other. And this has degree n. So any decision tree for AND must make n decisions. That's a proof. So this is a very classic work of two very famous people, Nissan and Szegedy. Sorry, not Szegedy, Szegedy. So now we are actually coming closer to the things that I am working on, the things that I am very interested in my research area. So now this is unique. So given a function, you will give me this polynomial, and you will argue, well, you cannot do better. If you want to have a decision tree, you cannot do better. But I might say, well, I am not so interested in exactly computing my function. I just want to be correct somewhat, not always, somewhat. So now we will see actually a lot of other notions where this polynomial is not exactly correct but has some error. It may be wrong somewhere, it may be wrong everywhere, but we will control its behavior, and that control of the behavior is what will actually give us power to be able to prove something about that polynomial. So we will look at some examples here now. So here is where I will actually need a little bit of notation. So if you do not understand the notation, you can ask me, but some of it might require a lot of time to explain. So I may actually ask you to refer it later after the lecture. You are of course welcome to talk to me after the lecture as well. I'll be actually we'll all be going to Ramanujan Hall, so I have to announce that later, but yeah, so we'll all be going there for tea, and you are free to talk to me. I mean, you are welcome to talk to me. So one thing we are going to allow is, well, you do not have to be correct on all points, just be correct on most points, right? So how many points do we have here? Can you count? 2 to the right, 2 to the n. So I will say just be correct on all except a small fraction. So I will say PA should equal FA on say 0.1, okay, some feedback, 0.1 times 2 to the n many a's. So instead of saying it has to be correct on all of them, it just has to be correct on most of them. This is a very useful notion which has been studied quite a bit, and it had already led to a breakthrough in an area which I work in, which is called circuit complexity. So some of the advanced students may have already encountered what is circuits. I mean, actually they are very similar to what you study in logic, AND gates, OR gates, you compose them and do some non-trivial calculation, but this has already led to advances in circuit complexity. So what this allows you to do is, well, you do not have to be correct on all points, so you can actually do more functions. What I mean by that is this: here you needed degree n, right? Here if you want to find such a polynomial for the AND function, you can find it of degree some, say, I will just say log n for now. This is not the correct answer, but in spirit it is. You can find it of degree log n, and log n is of course much smaller than n. So what I am saying is, just by allowing a little bit of relaxation, that you do not have to be correct on all points, you just have to be correct on most points, you can actually find a much smaller degree of the polynomial. Now why is this degree useful? So now again we have to go back to a property of polynomials which has to do with the degree and I will tell you one identity which of course I will not be able to prove in the interest of time, and maybe even afterwards I will not be able to prove, but so let us say you have a polynomial p of x where you know the degree is d, right? It's a single variable polynomial. So I will write this expression minus 1 to the I n wait. Yeah, so actually what you have is a bunch of points. So I will start with 0 because I am a Python programmer, so I start with 0. AD, you have these d plus 1 points, and you write this expression d choose I times p of ai. So this is a binomial coefficient, you know what this is, right? This is a binomial coefficient, and you write this expression, this will always be 0 for any polynomial of degree d. So in some sense what it is saying is, you look at these d plus 1 points and you take an average of the polynomial. If there is something I have missed maybe, okay, so yeah, maybe it is not really correct. Yeah, actually it is d plus 1, sorry, yeah, no, wait, okay, let me not write this identity because I am making some mistake here, I have forgotten what that identity is, but there is some expression, okay, so it is minus 1 to the I, some coefficient here, so think of it as a weight for the polynomial, some weight, and p of that point, this expression will always value to 0 no matter what the polynomial looks like. As long as you know that the degree is d, this expression will be 0. And a very similar expression you can actually write for polynomials over many variables, multivariate polynomials as well. So you can write a very similar expression, and what it is saying is that if you look at the polynomial and take an average value, right, so this is the weight, so it is a weighted average value, but if you take a weighted average value with this sign, so this sign is very important, minus 1 to the I, right, if I is even this will be positive, otherwise it will be negative. So you are essentially saying that if I look at these two parts where I is even, I is odd, they will cancel each other out. This is always true for any polynomial. So now the thing is that if the degree of the polynomial is large, for example x1 to xn, this expression will require very large numbers for me to represent, but if the degree is small, the numbers here will be much smaller, and I can talk about what these numbers look like, and I can talk about something called a vector space. If you know what a vector space is, I can talk about a vector space of these numbers, I can say its dimension must be small. So there is a lot of mathematics that you can use to say something about these polynomials because they always satisfy these identities. So the main thing you should remember from here is that polynomials of low degree always satisfy these identities. It does not matter what the structure of the polynomial is. and then all you have to show for a function is that it will not satisfy this identity. So let me restart a little bit. You had this set for which you found polynomials of small degree. You said polynomials of small degree always satisfy this identity. All I have to show is that a polynomial for g cannot satisfy this identity. And if it does not satisfy this identity, what can I say about the polynomial?
Large degree.
It must have degree larger than whatever I had here, because otherwise it would have to be 0. It had to satisfy this identity if the degree were small. So if it does not, the degree has to be large. So I will just so now this actually gives you a way to prove that the degree of a certain polynomial is large. Just have to show this identity is not 0, not being satisfied by the polynomial. So for example, in this model you are able to find much better polynomials to represent the AND function, which I said here. Then there is a very similar notion where you might say that this agreement is over a field, and I am not going to define it. Actually I do not have a lot of time anyway, but again it led to a very major breakthrough in circuit complexity. It was a work of, so actually you can find all of this if you just look for the polynomial method in computer science. Okay, if you want to read up about it, just look for the polynomial method. So all of this is actually covered in the polynomial method. There are many nice surveys. Now there are other notions you could say. I will say I don't care whether if the polynomial is correct on most points. In fact, it could be wrong on all points. I just want it to be close to my function. And by close, what I mean is I will look at these values PA minus FA, and I will look at the absolute value. So I will see how far are they as real numbers. Okay, and I will sum it up over all points in the Boolean, all Boolean points. I will sum up this number, these numbers, all the absolute differences. So P might not be correct on any of the points, but what I want is this number should be say 0.1 times 2 to the n. I could ask about this. And this notion of polynomials actually turned out to be useful in machine learning. So there is a work of 3 again very famous people, Linear, Mansour and Nissan, who used this notion to say that some functions have a easy machine learning algorithm. So if you want to understand what the function is, there is an easy machine learning algorithm that you can use to understand what that function looks like, and they use this notion of polynomials to prove this fact. And again, all of this is useful. Why? Like, why did they have to go to a polynomial? Why could they not do it directly? Just look at the function and do it. It becomes easier with the polynomial because you have so much more structure. They satisfy this identity. If you look at a significant number of points, it cannot be 0 on all of them. 2 polynomials must differ on a lot of points. So in fact, just 3-4 facts of polynomials satisfying this identity, they must differ on a lot of points, and that there is a very nice derivative and very simple continuous structure. Just these 3-4 facts come up almost everywhere wherever they study polynomials. And again here they just use the fact that, well, they must satisfy certain identities, and so you can essentially just look at the polynomial at a few points and understand what that polynomial looks like. But because you know the polynomial is very close to your function, you also know what the function looks like. So what's the problem with machine learning? What's the biggest problem for machine learning right now? Is it the machine learning models? Does anybody know what the biggest problem for machine learning is right now? Is it the size of the model, or is it the, it's actually the data. Yes, it's actually the data that they have to handle, and they cannot look at all the data. There is so much noise in the data, there is so much data to handle, cannot look at all the data. So they have to end up looking at few things from the data and actually be able to understand about the whole data. And you can see something very similar happens with polynomials. Just look at a few points, you will know what the polynomial looks like, and if you know what the polynomial looks like, it's very close to your function, so you can actually understand what the function looks like. And that's exactly the insight that they had. You can do all of this via polynomials. Another notion which I am very interested in is that on no point should it be too far. So instead of the sum, I am asking that if I look at any point, any Boolean point, the polynomial will be close to the function as a real number. And now here is where I can actually start talking about some open problems, because otherwise stating the open problems would, themselves would have required a lot of time, just many lectures, but here is a very simple open problem I can talk about. So first of all, of course, why is this useful? Well, again, all of those things about polynomials apply, but it's also useful for quantum computation. So just like with computation, we want to prove that certain computation model cannot do a task quickly, we also want to use it for quantum computation. We want to say that, well, there are certain tasks which are hard for quantum computers as well, and there were very few techniques, like very hard to find, for quantum computers to prove such a statement, and this turned out to be one of those techniques. So this has connections to quantum computation, and it actually has been studied for more than 30 years, this problem. It's one of the oldest problems in computer science. Lot of work has already happened, lot of work is even happening right now. You will see a lot of publications on this, very good publications in top venues, and in fact some people here are also working on them, and I am one of them. So but it also has connections to many other things like cryptography, like machine learning algorithms. So it actually has many connections, but this interesting thing I want to tell you about, which is it has connections to quantum computation. So if you want to prove something, that some function is hard for quantum computers to compute, you can actually use this model, say that the polynomial I can find which is close to the function on all points must have large degree, then that function will actually be hard for quantum computers to compute. So now here I will actually mention a very simple to state open problem, but probably a very hard problem. So I will define this degree, say r of a function, degree r of a function, as the minimum degree of a polynomial which satisfies this relation that I have defined already. So I will define this number which is the minimum degree that you can find for a polynomial which is always close to your function. And do you know how what function composition is? Right? Just take the value of one of the functions, put it as the argument of the other function. Now, but we have multivariate functions, right? So you would actually need a multivariate composition. So I have f which takes in a bunch of inputs, and all these inputs are actually a function applied over a bunch of inputs. So x1 to xn, let's say, then g2 is applied over y1 to yn, and some gm is applied over, say, z1 to zn. So you compute g values over these variables, and then you put them as the argument for f. The question I want to answer is, can you prove degree of f composed G is omega of degree f times degree G. That's all I wanted to prove. So in some sense it is saying composing functions is essentially equivalent to multiplying their degrees. If you want to understand the degree of a composed function, just multiply the degree and you will be fine. What we already know via a very non-trivial work is that this holds. So it's upper bounded. But as long as as far as lower bounds are concerned, there are results, but none of them come close to proving this for any f and g. So if there is one open problem that I want to take home from here, then you can take this home, but it's a very hard problem probably, or one of you might end up solving it. So there is definitely a best paper award for it, definitely, and maybe even more. And now one very interesting thing I want to tell you about here is that linear algebra comes in when you want to talk about these polynomials, and linear algebra is something that you will see in one of the later lectures. Hitesh might, he said he will talk about linear algebra in computation, and this is also one of the places where linear algebra comes in. I am not able to go into detail because of the interest of time, but now finally I just want to say last few things, then we will all go for coffee. So one thing is, I said, if you remember at the beginning I said that there is something I want to talk about if I have time. So I will talk about it here. So let us say you are given a function, a Boolean function, and you want to know, is there a polynomial that can represent it in this way? Is there a polynomial of low degree which can represent it in this way? So let us say I just take the exact computation model. I want to understand, is there a polynomial of low degree which can represent the function? I know that a polynomial must satisfy that identity, and because the function is equal to the polynomial, the same identity is satisfied by f. Make sense? If I look at the function, it is the same as the polynomial, so whatever identity is satisfied by the polynomial is also satisfied by the function. So I can just check whether this identity is satisfied. So what I know is that if the degree is small, this identity is satisfied. But what about the other direction? If this identity is satisfied, is the degree small? That's not clear, that's not immediately clear. But it turns out that most of the time, if this identity is satisfied, the degree will be small. And this actually came out of an area called property testing. So again, if you want to read about it, property testing is the right word to search. And then finally, this is the last statement I am going to say today. The area that I work in is actually kind of an intersection of property testing, this type of polynomial, but defined in a slightly more general way, and some more, if you know what Fourier analysis is, then it also has to do with Fourier analysis. So the area that I work in is actually an intersection of a lot of these things. And again, the question that I am trying to solve, I don't know how easy or hard it is, but to anyone who solves that problem, I am guaranteeing there is a prize for it. You know the Gödel prize? That prize you can probably get for that problem if you solve it. So it actually is in the intersection of some of these things that I talked about. Again, I do not know how hard or easy that problem is. I have been trying for quite some time. I have very little progress, but maybe one of you can do that. I will be very happy if you do. So that's it.